Good morning, professors. We're the team from Ying College. I'm Xinghong Lin, and they are my teammates, Yuyan Kan and Yuhin Li. Today, we are presenting our paper, The Game of Math, which studies how mathematics can be applied in decision-making in certain games. The main mathematical tools we use in this project are Nash equilibrium and Markov chains. So our project can be decomposed into two parts. The first part studies the lowest unique number game, or LON in short. In this part, we establish three main theorems which solve for the mixed strategy symmetric equilibrium for certain sizes of LON. And the second part studies the territories capturing process in the board game Risk, which is a Markov process. In this part, we calculate the entries of the transition probabilities matrices, which enable us to derive the winning probabilities once given the number of attacking armies and defending armies, in a more general setting of game rule where we allow the players using dice other than 6 faces. So here are our main results for the first part of our project, the LON. Theorem 1 is a useful lemma, which we'll cover in the next section. And Theorem 2 and 3 characterize the symmetric equilibrium for the N2 LON and for the 3M LON. In this process, we also discover an associated sequence which is useful for calculating the equilibrium. These two theorems give the solution of some finite size of LON. And for Risk, we construct a Markov chain model that extends the usual rules of dice to include arbitrary numbers of sides. Applying this framework, we explicitly derive formula for the transition probabilities as shown in this table. In particular, we may compute the winning probability and expected loss of attacking a given territory. This allows us to quantify how costly an invasion is under different configurations. So let us first start with the LON. In this game, each of the n players simultaneously chooses from a finite set of m integers, and the winner is the player who chooses the smallest unique number. And some examples are provided in this slide to illustrate how the winner is determined. And some notes worth mentioning is that we will find out the solution with the concept of symmetric Nash equilibrium, in which no player can increase their winning probability by only changing their own strategy. In particular, we characterize the symmetric equilibrium for the N2 LON and for the 3M LON in the followings. And we show that in symmetric equilibrium, all coefficients of numbers are equal. Here are some notations we will use for the game. In particular, WIS here is the win rate of player xi, which can be expressed in terms of Pij, the probability of player I choosing the integer j. Then when one focuses the problem from player xi's perspective, he may regard Wi as a polynomial in his own strategy, while grouping the other terms as a coefficient, alpha j. We focus on symmetric equilibria, and we do not consider asymmetric ones because, in practice, it is unreasonable to pre-assign a special odds strategy to a particular player. So here we recall the three main theorems for LON. We'll outline their idea of the proof rather than going through our computation details. So starting with Theorem 1, it states that in a symmetric Nash equilibrium, the coefficient alpha j of all numbers are equal. So here we prove by contradiction. Assume that a coefficient is strictly larger. A player can increase their winning probability by choosing the corresponding number more frequently without changing anyone else's strategy. This contradicts the definition of an equilibrium. Therefore, in a symmetric Nash equilibrium, all coefficients must be equal. So consequently, since the probabilities of all numbers sum to 1, the common coefficient for choosing any number must equal the overall winning probability of player xi. So next, we move to explicit solutions of certain finite LONs. Starting with Theorem 2, where we have at least 3 players and only 2 integers available, the symmetric equilibrium is a strategy where both numbers have the same probability to be chosen, which is 0.5, and the winning probability of a player is 0.5 to the power n minus 1. Here we prove by considering the winning conditions of a fixed player. With the symmetric strategy, and with Theorem 1 stating both the coefficients of probabilities are equal, we can prove that P1 equal to P2, and the winning probability can be found through direct computation. And finally, we consider the most general LON setting in our work, 3 players' arbitrary finite set of integers. We found out the solution of the symmetric equilibrium strategy is related to a recurrence relation, in particular this expression. Here, the outline of this proof is that we first classify the situation for a player to win, which is when both other players chooses a larger number than ours, or when both the other players chooses the same smaller number. Then comparing the coefficients corresponding to number I and number I plus 1, using the fact that they must be equal in symmetric equilibrium, we obtain equations relating these probabilities. From this, we can deduce that PM equals to PM minus 1, while all other probabilities are in a fixed ratio. Hence, we define lambda I as the ratio of the I minus 1th largest probability to the ith largest probability. And carrying the calculations through, we find out that lambda I itself satisfies a recurring relation, and all the probabilities can be directly computed explicitly. So it gives a complete solution to the game. So this part of calculations show that the probabilities are actually in ratio. And these note will simplify some relations in our next slide. And these part of calculations is how the recurrence relation arises. With these and some direct computation, we can finally solve the game in the symmetric equilibrium state. And some numerical values of the sequence lambda I is also provided here. So in the remaining time, we will transit to the game risk, where we use Markov chains to analyze the expected loss and success rate of attacking a territory. In case you are not familiar with this game, an important part is capturing territories based on a sequence of dice rolls and value comparisons. Two players will roll dice iteratively until all armies of one side are eliminated. Our main findings are to extend game rules to include arbitrary dice sides, denoted as S and T for the attacker and defender respectively, and find the explicit formula for transition probabilities. Here are also some notations we will refer to in the following. And also for simplifications of calculations, we assume that S is smaller than or equal to T. So as dice rolls in the game is about a Markov chain between states, which in this case is the number of armies on both sides, we should first define the transition probability matrix P. It adopts the block form shown in the screen. In particular, Q is the matrix encoding the transition probability between transient states, and R is that from transient state to absorbing states. So the game consists of many different transition probabilities between states according to the dice count of both sides, which we will refer to as cases in the following. And to simplify calculations, we will break down each of these cases into smaller subcases and establish relationships between die. We will take the most complicated case of 3 attacking die versus 2 defending die in the following. On the screen, you may see the different scenarios if there are 3 attacking die and their respective probability density. Specifically, in this case, as the number of dice compared is kept at 2, we will sum up the probability of different Y3 values to get table 2. These probability density formulas could be calculated using combination and permutation methods. And the same could be done for the defender. As there are 2 scenarios for both the defender and the attacker, we get 4 subcases to evaluate in the following. Specifically, we will demonstrate the case where the attacker wins over both defender die. We decompose the probability into 4 subcases according to the table in the previous slide, and their probability formula are listed here in the following. These subcases are evaluated by some hard work and counting methods. The first 2 are displayed right here. And the remaining 2 subcases are displayed here. The other cases can be evaluated via similar methods, and we get our table. The probability for different cases are summarized by this table, where L1 and L2 are separated due to their complexity. So by plugging in the corresponding formulas from the table above, we may get our matrix Q and R, which we did not display here due to their varying size. And if we want to determine the winning probability and expected loss, we may simply look at the last row of the resultant matrix by observing the formula here on the screen. So above is the outline of our paper. In conclusion, through the aid of the Nash equilibrium and Markov chain, we deepen our understanding in our research topics. The main takeaway is that we learn how mathematics is a powerful tool in daily life, especially in complex daily life scenarios and games. For future directions in Long, we would like to further extend our study to find out a closed form for the symmetric equilibrium strategy that a player should adopt and evaluate more general cases of the game. In Risk, we would like to modify the map and connections based on graph theory, as well as modify game rules for an in-depth study regarding how dice counts and sides actually affect the whole game process. Thank you.